So in the first week, we started with the history of integrated circuits, where initially were vacuum tubes. Initial were vacuum tubes made as diodes and triodes. The difference between both, so the diode had an anode and a cathode, and where a triode had a grid in between, which could be used to control the flow of current. So a triode could act like a transistor. This was followed by a solid state transistor, and then the first IC by Robert Noyce. So then we learned Moore's law, where the number of transistors in an integrated circuit doubles every 2 years, and till recently the Moore's law has been followed, but right now it's slowing down due to physical limits. Yeah. So then we learned that so we learned that the sizes of silicon wafers that are used right now. We are using 300 wafers, that is 12-inch, and in the next generation, soon we will start using 16 or 18-inch wafers. And then there are interconnects that connect between different levels of different levels, metal interconnects that connect between different levels of an integrated circuit in the back end of the line. Right now, the 11 interconnects are being used. Then the overview of IC fabrication, in which the first part is material preparation, where we start with sand, then we convert it to silicon, then from then from silicon we get polycrystalline silicon, which is EGS. Then crystal growth and vapor preparation. From polycrystalline silicon, we we grow single crystal ingots using Chorlsky or float zone method, and then we cut the ingot, slice the ingots as single wafers. Then we polish the wafers. Next part is wafer fabrication and assembly, where on each wafer the integrated circuit is fabricated, including interconnects. Then the dies are sliced as individual dice, and they're then sorted according to defects. Then there then these individual dice and chips are then packaged, wire bonded and packaged as a single device that can be used as an end product. And then after packaging, the final electrical testing of the packaged devices is done at the consumer end, not consumer end, but now silicon wafer manufacturing. In starting materials is quartz SiO2, which and from that we use a submerged arc electrode process. So in this you add different SiO2, converts into SiO, then that SiO then reacts with carbon to produce SiO2, and it, SiO2 reacts with carbon to produce SiO. That SiO then further reacts with carbon to produce SiC, then that reacts with S to get SiO2. So this is a looped process. Ultimately, the SiC and SiO2 react to give silicon and more SiO and CO. So you can see this is a completely loop process. So in the end, the silicon that you get is then taken out of this reaction, as in, then this is called metallurgical grade silicon. So only 2% of this metallurgical grade silicon is used to produce the electronic grade silicon, and that is done using Simon's process, where MgS and HCl are mixed in a fluidized bed reactor to get SiHCl3 and other other hydrochloride complexes, which are then which then undergo distillation to separate out HCl SiHCl3, which then undergoes this Simon's process, where where you use thin silicon rods on which the SiHCl3 breaks down and into SiCl4, and then it reacts with in the gases in the chamber to get silicon and HCl. The silicon gets deposited on these rods, and then HCl is then reused to react with SiHCl3 and Cl4 to get to make it a looped reaction to get more and more silicon. So this silicon that is deposited is called electronic grade silicon, and it is polycrystalline in nature. The impurities are in ppm level here, and then using Chvalsky or float zone process, it is converted into crystalline silicon, a single crystal silicon. In this molten silicon and a seed silicon crystal is slowly pushed up, and it creates this ingot. In float zone, there is a heated zone. As it goes up, it melts the polycrystalline rod in between, and as that molten rod then gets cooled down, it cools down in a crystalline form according to the seed crystal attached. The benefit of float zone is that there is no interaction of the ingot with the side walls. There are less chance of impurities, but this process is limited to only very small thickness wafers like 2 inch. Then the ingot is then sliced into individual wafers, and then the wafers are flats are cut into that wafers according to the type: P type 111, P type 100, N type 111, N type 100. It helps in easy identification of the doping and orientation. Then this is the overview of fab operations. There are 4 types of fab operations: layering, doping, patterning, and heat treatment. And each integrated circuit is inserted as a form of so each wafer is divided in form of dies. Each die is an identical integrated circuit. After the fabrication process over, it will be cut. The cut die is called chip, and the lines along which they are cut are called script lines. The the chips which are on the edges and are not fully formed are called edge chips, and they are usually wasted. And this is an overview of a MOSFET. You start with a wafer, you grow field oxide, then you mask it and grow gate oxide, then you deposit polysilicon, then you etch it to make your source drain mask. You dope your source drain regions, and then reoxidize it, and then pattern it with and grow your metal contacts. So this is your final MOSFET. So Now we come to week 2, where you learned individual fabrication operations. First is oxidation, in which the silicon substrate is heated in an oxygen environment. So they can, in a furnace at high temperatures. So if it is reacted with O2, it is called dry oxidation, and if it is reacted with water vapor, it is called wet oxidation. Wet oxidation is much faster than dry oxidation. So if you want a very thick oxide layers, you go for wet oxidation. Want if you want thinner layers and you want control over the reaction, you go for dry oxidation. The since silicon is converted as to silicon oxide, the amount of silicon reduces, and that the thickness of silicon that is converted to silicon oxide is given by this formula, d dash equals to 1.88 d. This is the for oxide growth regimes. For thin oxide, you follow a linear growth regime, and for thick oxide, you follow a parabolic growth regime, where in thin oxide the thickness is proportional to time, and in thick oxides the thickness is proportional to square root of time. In thin oxides the growth rate does not change with time, and in thick oxide the growth rate decreases with time. It is growth rate, not growth. Remember that growth and growth rate are different. Here the reaction is controlled. Here the control is through reaction, and here the control is through the diffusion process. Then next is doping. Doping is done by two methods: thermal diffusion, ion implantation. In thermal diffusion, the dopant atoms are at high temperature. The dopant at the wafer is kept in a dopant atom environment at high temperature. The dopant atoms diffuse into the wafer surface, and they can be all as solids, liquid, and gases. And the maximum concentration you will find at the surface, as you go deeper, the concentration will decrease. In ion implantation, you don't have to increase the temperature. You you give you give energize the dopant ions using voltage guns, and you bombard your wafer surface with the high energy ions. The ion the ions then impinge themselves into the wafer surface, and so based on the maximum energy of the ions, you will see at some particular depth there will be maximum concentration of ions, and both upside and downside the concentration will reduce. So thermal diffusion is diffusion control. So this is the diffusion equation. D is equals to D naught exponential e, raised to power minus EA by KBT. EA is your activation energy, and KBT is your temp. Hello.
क्या बना ये? Sorry, sir. Sorry, sir.
Yes.
Continue, sir.
Okay. Okay. So KB is your Boltzmann constant. T is your current temperature. So and liquid or gaseous sources, your the we consider it as a semi-infinite source. So the concentration of the source in the environment is not reducing. So your surface concentration is equal to the concentration of the environment. So it remains constant, and the final concentration is given as an error function, where x is your depth, d is your diffusion, t is time, and cs is your surface concentration. In solid concentrations, the concentration of the source in the environment will reduce. So hence your concentration at the surface will also reduce with time, and you will get a Gaussian solution where your surface concentration at particular time is given by C of 0 t comma t, and your at x comma t, at x depth it will be given by x e raised to power minus x square by 4 dt. This is a this is just an image of how an ion implantation instrument works, and this is your depth doping profile you get in the as an ion implantation method. The position where you get your maximum concentration is called range, and the depth is your position till where your dopants have impinged. And so in diffusion, since it's a high temperature process, the the particles are itself embedded into the lattice structure of the silicon, but in the ion implantation the dopants are just impinged into the lattice inside the crystal wafers, and they are not sitting at the lattice position. So to make them so they to make them replace the silicon atoms in the lattice positions, you have to do post implantation annealing at high temperature, so that the dopants replace silicon at the lattice positions, and that way they can behave and they can become a part of the crystal structure. Next is your lithography, where first you planarize your surface, then you apply your photoresist as a by spin coating, then you do soft bake where you heat it at some temperature so to remove the solvent inside the photoresist, evaporate the solvent, and thicken your photoresist, solidify the photoresist. Then you place it under a mask where some portions are exposed and some portions are not exposed, and then you expose it under UV light. So then you develop the resist based on whether it's a positive or negative resist. Some the exposed portions will either remain and the unexposed portion will be removed, or the unexposed portions will remain and the exposed portions will be removed. Then you do a hard baking to fix the pattern, so so that you don't lose the pattern during further processing. Then you do resist inspection, that is whether the development has gone properly and the features are as per your requirement. Then you do your etching where the part that is not covered by resist will be etched, and then you remove the resist, which is also called resist stripping, and then you do your final inspection, that is whether the etched parts are as per the design. So then we come to positive and negative resist, where positive resist becomes soluble in developer when it is exposed to light, whereas negative resist becomes less soluble in when exposed to light. So if we have applied positive resist when we put it in developer, the exposed part will get removed and the exposed part will still remain. That means the pattern that was there on the mask will be the resist pattern remaining. In negative resist, the exposed part will remain after development, while the unexposed part will be removed. So the resist pattern that you get will be negative of the pattern that you had on your mask. So the resist is deposited by spin coating, where you place your resist on your wafer and then you spin it at certain rotation speed, and the excess resist will get removed from the wafer surface, and some thickness of the resist will be evenly coated. So if you have applied small amount, you won't be able to cover completely resist. If you apply very high amount, the resist there will be resist that will be coated beyond the sample surface, which and it will be coated underneath the wafer surface, which will cause issues during lithography. So for very very small patterns, we can go for e-beam lithography, where instead of light, we use electron beam as the exposure part. And since electron beam have very high energy frequency, very small wavelengths, they can give features in nan they can give features in nanometers, which is not possible in photolithography without special tools like steppers, so that we can see here. So typically the resolution, which is the minimum feature size, is given by in a photolithography, is given by k lambda by na, where k is a constant, lambda is your wavelength of light used, and na is the numerical aperture of your lens used. So to improve resolution, you can either reduce the wavelength. So initially we were using 365 nanometer. Right now they have gone till 190 nanometer deep UV wavelengths, which is extreme UV lithography. And you can also increase the numerical aperture by by using immersion lithography. So that will increase your mu, which is your refractive index. And there are other methods such as double patterning to improve the contrast. You you pattern you do a positive resist and a negative resist patterning that helps you improve the contrast. That is your for week 2. For week 3 we have etching. So in wet etching, your wafer is kept in a etchant solution, and the exposed surface will react to the etchant solution, and that will cause the your wafer exposed part to etch away. The react with it will react with the etchant, and it will get removed into the etchant solution, while the covered part that is covered by the resist will not get harmed by the etchant solution. It is an anisotropic process. That means it 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 reacts according to the wafer plane. So in some part, for silicon etching, silicon oxide or silicon nitride are used as masks for to because they are not harmed by their etch rate in the silicon etchant solution is very 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 low. That can be seen here. The etch rate for silicon nitride in phosphoric acid is at hot phosphoric acid is only 8 nanometers per minute, whereas for silicon it goes very very high, 100 or even beyond. So now you can have, so normally you will have, because the etching is done in all directions. You will have some undercut below your below your mask. So you will have some area that will be etched. if if you keep it for long time, you will get further etching, and that will so after a long time, the all the material below your resist will get etched, and the resist will get removed, exposing the whole surface to your etchant solution, and it will cause you to lose your pattern. In dry etching, you use a gas plasma to etch your surface. It has it is slower than wet etching, but it has a higher directional control, and it is so for different materials, different plasma gases are used. So dry etching is dry etching is a diffusion control process where the gas atoms will surface of the diffuse to the surface of the wafer. Then they get adsorbed, not absorbed, they get adsorbed on the wafer surface, and after adsorption they will react to the exposed part and create the products. The products are then desorbed and diffused into the environment. There can be two types of dry etching: plasma etching or ion beam etching. In ion beam etching, the inert ions like argon gas, they are energized to high energies and impinged onto your wafer. They they hit your wafer surface and take out material with because of their energy. It is a physical process, and therefore there so in plasma etching, it is a reactive process, it is chemical process, so there is material selectivity. But in ion beam etching, there is no material selectivity. The high energy ions will remove every material present on your wafer. So but it the benefit of ion beam etching is that it is highly directional. So to combine the best of both, we use reactive ion etching, which has both physical etching as well as chemical etching, to give both selectivity and directionality. Next, we go for deposition processes. First is chemical vapor deposition, in which your
Sir,
yes,
excuse me, sir.
yes, yes,
Sir, in previous, just go to the previous page, sir.
yes,
Uh, another previous.
yes,
Yes, in this, you told this is not absorption. This is adsorption.
yes.
Means what is this?
So in absorption, basically your material goes inside your so if I am absorbing something, I am taking something inside me.
Yes, sir.
So
And at
adsorption is at the surface. So like you see, when you wash your hands, water is on your hands. It is not inside your hands.
okay,
Water
sir.
is sticking to your hands.
Okay, sir.
So similarly, that adsorption is a similar process. So it is not part of you, it is just on you. There is a physical bonding. It is just
Okay,
connected
sir.
to you. Yes. So this is chemical vapor deposition, in which you place your wafers in a high temperature furnace, and you give your precursors in form of gases ga- gases or molten forms, the the precursors get absorbed. Here similarly, either the precursor will react in the environment, or they will get absorbed on the wafer surface and react there, and they will form. After reaction, the product form will get deposited on your wafer surface. So you see, in adsorption, there is no proper bonding. It is just sitting there, technic kind of. So it will eventually get dissolved. Under some conditions, it will get dissolved. That is, it will go back to the environment. But after the products are formed, the products sit on the. They are not just sitting; they are deposited. They are like they have made a bonding with your bottom material. Some physical or chemical bonding they have made with the material that is already with your substrate. They have made a bonding, so they are not easy to remove. That is deposition. In adsorption, the removal process is very does not require much energy. They are just sitting there. That is your adsorption. So the in input precursors will react in the environment, and the product will be deposited on your wafers. There are multiple type of CVD chambers. One is this where the gas is coming from below. Next one is this where the gases are in a vertical position. Sorry, the wafers are in a vertical position. Another method is molecular beam epitaxy, where your substrate is on a rotating stage and your individual elements are in effusion cells, where this is in under very high vacuum, ultra high vacuum. So when you when you remove the shutter, the material inside will just direct go straight and sit on your substrate. So like if I remove shutters of gallium and arsenide, I will have gallium and arsenide directly coming out and sitting. So since it is an ultra vacuum, so there will be no diffusion in the air. They will just go straight, and when they go straight, they will hit the wafer, your substrate, and they will sit on your substrate and make a film there. That is how molecular beam epitaxy works. So generally, your substrate has a similar lattice to what the film you are growing. So the so the material film growth is epitaxial, that which means they will be lattice matched with the your already present substrate, and hence they will create a crystalline film. Next is your metallization, where you first create a pattern on your wafer, and then you deposit metal on your wafer, and only the part that is not covered by the resist or the mask will have the metal remaining. Ultimately everywhere else the metal will get removed as the mask or the resist is removed. This is done as part of the back end of the line process. So the front end of the line process is all your transistor and IC fabrication part. It does not involve any metals. So your polysilicon is used. Highly doped polysilicon is used to create the contacts, and then yeah, then your as back end of line process, metal are deposited only over the polysilicon parts, so to make the contacts. So the isolation is so because the metallization is done using copper, and copper can create defects in your silicon wafer. So to isolate it, we deposited dielectric layer over your an interlaid dielectric over the whole IC, and then we open areas on the contact regions, and do we then do the metallization. So this way the copper does not come in contact with any of your circuitry, the your wafer circuitry. So metallization is usually done by physical vapor deposition technique. There are three types: thermal evaporation, e-beam evaporation, sputter deposition. In thermal and e-beam, both are similar. Your material that you want to deposit is evaporated and in high vacuum, and as it and the gaseous atoms after evaporation just go and sit on your wafers, which are placed at high positions. The In thermal evaporation, the crucible in which your material is kept is heated to high temperature such that the material gets evaporated. In e-beam evaporation, the high energy electron beam is hit on your metal surface, and it creates a molten zone on the surface, and from the molten zone gaseous atoms are released that goes above and sit on your wafers. In sputter deposition, high energy argon ions are hit to your metal target, make and cause metal ions to get removed from your metal molecules to get removed from your target, and under DC bias or RF bias they travel towards your wafer and go sit there. Next is your metallization. Your so for metallization you do first do planarization to create to remove any kinks crest or troughs in your surface, and make it a plain surface so that it looks clean and the further process is cleaner. It can Planarization can be is done by chemical mechanical polishing, which has a both physical and chemical processes. And there are two types of generally two types of metallizations: trenches and vias. Vias connect two different metal layers, and trenches are used to make connections within the same layer. And then chemical and the metal layers are divided by interlayer dielectrics, and then the planarization done by chemical mechanical polishing. It's I think it's in the next part. So then then your metrology process control, in which you do metrology, electrical measurements where you measure the resistivity of your sample. This is done by four probe measurement, where you have four equidistant probes. The outer two probes are used to give a constant current, and the inner two probes are used to get the voltage output. And using this formula, your where your T is the thickness of the junction, thickness of the layer film, and V is the output voltage, and I is the constant current given, you will get your resistivity here, the resistivity of your film. And if you do a if you do a if you cut your wafer in like this and do at different depth positions, you can create a resistivity versus depth profile, which can be used. Since your resistivity will depend on your dopant concentration, So you can use this formula to get your dopant versus depth profile also. Next is the thickness measurement, where you have to measure the thickness of your oxide or other films. So this can be done using profilometer. In a profilometer, you have a stylus which is touched on your wafer. You can see here, and as it moves around, the height changes in the stylus are recorded, and that is used to give your step height measurements. Another is your interference measurements, in which your incident light is reflected from your top of the film surface and the bottom of the film surface, and the reflected light then creates an interference pattern, and then the number of fringes that we obtain can be used to determine the for two number of fringes for two different wavelengths can be used to determine the thickness of the film. Next is your defect detection. So you can do defect detection using methods such as incident light, microscope, SEM, Auger spectroscopy, ESCA, reflectance measurement, etc. to two different types of defects. This is an optical particle counter which can count the number of particles emitted from a particular region. This is a scanning electron microscope in which your electron beam is an electron beam is thrown onto your wafer, and the electrons that are backscattered are kept put in a detector. So based on the position where the electron beam is hitting, the output the scattered electrons will be different, and that will give us a semi image which can used to see different very high resolution images of your surface, and it can provide your defect density, defect sizes, as well as composition of your material. And since SEM does not hurt your wafers, it can be used inline. That is, it can the after your wafer at any process can go into SEM, and then go back to your fabrication in an offline process. Once the wafer goes into an offline tool, it cannot go back into the fabrication process, and it is then discarded. That is in your week 4. So process evaluation is done at 3 stages: at fabrication stage, at post fabrication stage where the dies are cut, and after packaging, where once the dies are packaged, you test the packaged devices. So, and the net yield is measured for fabrication. Your fabrication yield is wafers that have come out of the fabrication process to your die cutter, and divided by the wafers that we had in the starting before fabrication starting. Sort yield is the number of dies you had on each wafer, and the number of dies that you have that are functioning after cutting. Then packaging yield is the number of good dies that we had started for packaging, and then the packaged devices that pass the final parametric test. So fab then again, fab yield is divided as individual station yields. A station means each individual fabrication process. So the more the number of process that is the number of wafers that leave the process divided by the number of wafers that we had in the starting of that particular process. So you can see the higher the fabrication processes, the lower the number of yield you will get. The Since it's a multiplicative process, and no process is gives 100% yield. So even if we consider 99%, 99.999% yield, if we have hundreds of processes, that will create an exponential effect and the total fab yield will decrease. So the best to have a minimum number of processing steps. The other the other proc- the other things can be your wafers may break during processes, or they may get damaged, or there is some variation during the process like temperature, humidity, which cause your process parameters to change, or there were some defects during the processing. There were some defects during lithography on the mask, like uh, if your mask was broken, had a broken line or something, that will reflect in your wafer. So next is yield models. So there are four types of models that are used. Poisson model, where the defects are randomly distributed on your wafer. Uniform distribution, where the defects are equally uniformly distributed over the wafer. Next is your triangular model, where the defects are distributed as in a triangular manner. And your seeds model, which means that there are more there will be more regions with less defects and there will be less regions with more defects. It's a decreasing exponential model. Where your f of d is your defect density function and d is your defect density. So yeah, next is your wafer fabrication cost. So the fabrication cost will be determined will there are two types of fabrication cost. One is fixed cost, which does not depend on the number of wafers being produced. So your fixed cost is your labor cost and your equipment cost, and the fluid costs are the costs that are dependent on the number of wafers produced. That is your bill of materials. That is the number of the materials being used, the masks that are being used, the design costing, the overheads that you have, the sorting, and the that the cost spent on the sorting, the yield that comes in your other cost. So your cost is per wafer is given by this formula, where your $f means your fixed cost, $v means your material cost, labor cost, and the cost that process cost that when like your overheads when the tool is running. Your y is the cost of wafers that were scrapped due to defects, which is divided by the costs that are equally divided. That is your lifetime of the tool, your throughput of the wafer. That is how many wafers you are giving per per particular time. Your yield factor, that is what the yield you have got, and your utilization factor, which means how much how much tool is being used to produce n number of wafers. Next is so the fabrication is done is the Methods to reduce your defects is your clean room. So you want your clean room to be as as dust free and as particle free as possible. So your clean room is classified by this ISO classes. ISO 1, for one cubic meter of air, there should be not more than 10 particles which are greater than 0.1 micrometer in size. For in class 4, there should not be more than 10,000 particles greater than 0.1 micrometer size per cubic meter of air. And this was the earlier classes that were used: class 1, class 10, class 100, class 1000, which were the US federal standards. And this is how the particle concentration is given for particular particle sizes. Like here we have, for 1 micron size, there should not be more than 83 particles per cubic meter, and for in a class 4 environment, and for 0.1 micrometer size particles, there should not be more than 10,000 particles. So next is how the clean rooms are designed. So for this is how a wafer workstation is. So this is where, this is the top, this is a side view. So on the top you have your blower, which which flows with which provides the air in through a HEPA filter. A HEPA filter filters the air and removes the maximum number of particles, which then go the then the air goes into your wafer workstation, and from the outlet it goes out, and this way it's recycled. This is another method which shows laminar design, and this is how your clean room ballroom design is, where there is perforated floor which takes out the air. It goes to your service area where the fresh air goes in, and there's a region above which takes in the air from their service area, makes it go again through the HEPA filter into the clean room. This way the air is recycled, and this is how your process tools are designed. So they are kept under high vacuum environments to reduce the amount of contamination as much as possible. So these are the pumping systems for the vacuum. So your wafers come in through a isolation pod. They are mechanically attached to your tool. The door is opened, and you have a load unload chamber with a robot arm, which take which will take in which will go into your isolation pod, take out your wafer cassette. Then it will close this chamber, and it will open this. It will pump down. It will pump down so that any environment, any contamination that was brought in by the isolation pod is removed. Then the robot arm takes the wafer cassette in your process chamber, and there is again an environmental control chamber to isolate isolate the wafer load unload chamber to your process chamber. This way your process chamber is completely isolated from your outside environment, and this is how you stay contamination free for at such small scale. Then we come at passive circuit elements, that is resistors and capacitors. So there are three ways to make a resistor, which is one is a doped resistor, where you dope certain region of your wafer to create a resistance, and then contacts are made on each end of the doped region. Next is your linear transistor, where a straight line is deposited on your wafer, and the contacts, these are the contacts. Then a serpentine resistor, where you make a snake like structure so that you have a longer line and the same same footprint, so that you have more resistance. Next next is a capacitor. You can have MOS capacitor, where you have on your semiconductor wafer you grow an oxide, and then the metal contact is grown on your over your oxide, and then a metal contact is taken directly from your wafer. So this is our metal oxide semiconductor MOS capacitor. So this oxide acts as the dielectric between your metal and your semiconductor, and that gives your capacitance. Or you can create a trench inside your silicon and fill it with dielectric material, that is oxide, and in the middle you have a thin polysilicon metal. So this polysilicon uh, silicon oxide and your silicon, this creates a capacitor. Then active circuit elements are elements which control the flow of the current, that is your PN junction or Schottky junction or transistors. So PN junction, you in your end, suppose you have an n-type wafer, you dope a part of it as p-type. So the p-type region and the n-type region will have a junction in between, and then you create contacts from your p side and your n side. That will your PN junction. A Schottky junction is created between a metal and a semiconductor contact. So directly you make your contact from your wafer, and a metal take a contact from your metal. So this metal semiconductor interface will create a Schottky junction, which is caused due to band gaps, sorry, band structures. Next is your transistor. So this is a BJT, bipolar junction transistor, that is your PNP or NPN transistors. So here you can see your this is your lateral PNP, where one contact is taken from your substrate, the one contact is taken from your epi layer, and then one contact is taken from your doped region, PNP. This is vertical region, where this is your PNP, and here it's a lateral. So one contact is taken directly from your n-type emitter. One then there these are doped. These are two doped p types, which are so this is PNP like this laterally, and these are vertically. Next is your MOSFET, that is metal oxide semiconductor field effect transistor. This is here the I've already shown you how the it's made. So here you have your polysilicon gate, you have your SiO2 as gate oxide, and you have your silicon as your transistor channel material. So in a p-type wafer, you have your doped n-type regions which act as your source and drain. So when you bias your gate, that will create a field effect in this region. And so right now, since it is these are N and this the middle region is P, there will be no current between your source and drain, and and you can say that the transistor is in off condition. But as you change your bias on your gate, that will create a field effect in this region and convert this region into an n-type material by depleting by increasing the number of electrons in this region, and that will create a path from your source and drain, and you will have a conducting area conduct you will have a current between this region, and that is called your on state. So next is your logic gates. You can make logic gates by using diodes or transistors. So this is how you make a OR gate using diodes. You have two inputs on P P end of the diode, and they are commonly connected to your end of the diode. So when here 1 means a high voltage and 0 means a low voltage or negligible current. So and if you have a current here or a current here, the or a current in both of them, you will have a current in the output. So only only when there is no input, then only you will have no output. So that is how it's an OR gate. That is, you will have only when zeros input 1 and input 2 are 0 0, the output is 0. In all other cases, the output is 1. Similarly, you can create it using transistors where the input is given to your gate and the output is taken through your source and drains. Similarly, you can make an AND gate by reversing the diodes. Inputs are given to your N region and output is taken from a P region. Here, only when both inputs are high, the output will be high. Or in all other cases, the output will be low. So that is how an AND gate is created. Next is your packaging. In packaging, you have to you place your die in middle, and you have to connect it to the legs, which these packaging legs, which make your con which are used to contact with the external devices. So the contacts on your die have to be connected to these metal legs. And this is called wire bonding. So wire bonding is can be done by two types: ball bonding and wedge bonding. In ball bonding, the on your on your die contact, the wire is placed in form of a ball, and in wedge bonding, the wire is placed in form of a wedge. The contact is formed like as a wedge. Next can be done by tape bonding, where you place your metal metal leads on your contact pads, and you place and you perform pressure on it, so that the leads get stuck to your pads. Next is a flip chip bonding, in which you create your contacts on your packaging like as solder bumps, and you play and on each of the in the pattern that is similar to the pattern you have on your wafer die. And when you place the die on your package, they create a contact using the solder bumps. That is called flip chip bonding or C4 bonding. Next is this is a packaging type. This is called CRDIP packaging, in which a plastic lead frame is used, and the your contacts are wire bonded to the legs, and then top casing is put. So this is the overview